Hi, welcome back. I'd like to continue with the systematic sampling today. Earlier, we talked about how we estimate the mean under the systematic sampling. And the mean estimation would very much heavily depends on the distribution of the population itself. So if we have an ordered populations, using a systematic sampling could improve our estimation, because we try to capture the differences within the sample that we collect. So that's why we say our systematic sampling is indeed a special case of the cluster sampling, that we want the sample that we collected within the sample or within the cluster, we want it to be heterogeneous. So we want the variation could be slightly larger within the sample. And then between cluster, we want it to be homogeneous. So they could be quite similar between the different samples, different cluster that we collected. So this is the total opposite from the stratified random sampling in chapter 4. Okay, now I want to continue with the variance estimations. And again, this is very important that we understand the population distribution. Then we can apply the variance estimate for the systematic sampling. Okay, so before I go into that, I would like to emphasize that since we mentioned the systematic sampling is a special case of the cluster sampling, because we only select one cluster from the population. Why is that? If we are imagining from a population and then we select the sample systematically, so we can only have one chance to pick one in-cave sample from the population to be included in my sample. So at the end of the day, I only have one set of sample collected from the populations. So in this case, we are not going to, in reality, we are not able to collect different sample y-bar and look at the variation of the y-bar or the distribution of the y-bar collected from systematic sampling. So we are not being able to estimate the unbiased estimator for the variance of the y-bar under systematic sampling, because it does not exist. Because at the end of the day, we only select one cluster at random, and we cannot estimate the variance based on one sample. In this case, under systematic sampling, what I can provide is a different methods of estimating the variance from the systematic sampling. We would use a simple random sampling method. We would use a repeated systematic sampling, our half size, and differences method. Okay, so in the following, we'll talk about that. First of all, we can use simple random sampling method. So assume that the population itself is quite randomly distributed. So whether we select the sample randomly or we select in a systematic way, it does not matter. Okay, so we pretend we use a simple random sampling of, let's say, even though we select the sample in a systematic way, but at the end of the day, we would say that the population is quite randomly distributed. So we can still calculate the estimated variance from the sample, that based on assuming the population is quite randomly distributed. So using the same formula from chapter 3, we can estimate the variance of the y-bar as for the systematic sampling. Okay, and we use the same formula for y-bar, which is the final population correction factor multiplied to the sample variance divided by m for the y-bar, for the total, and for the proportion as well. So since the variance estimate of the systematic sampling from an ordered population with large negative correlation produce more precise estimate than the simple random sampling. So in reality, if the population itself is an ordered population, using this set of the formula would overestimate the true variance, right? But that's the best we can do. So if that's the case, we can always say that if I select the sample using a systematic way, but if I use this set of the formula to estimate the variance, that provides an upper bound for the variance. Okay, it's overestimated true variance because we would have achieved a more precise estimate, but we can't do anything about that. So what we can do is to provide an upper bound for the variance estimate if we use the simple random sampling formula. Secondly, we're not happy with that, so we want to think about that based on the systematic sampling that we collected. Can we try to put it into a different ways so that we would have more than one systematic sampling? That's why we introduced the section 5.6.2. This is called the repeated systematic sampling scheme. So what does that mean? It's like if originally from the population we select every 10th item. Let's say population, we have our 100 population, and then we select every 10th item. So at the end of the day, I would have 10 n, little n equals to 10. My sample size equals to 10, right? K also equals to 10 because I select 1 in k items. But if I do a repeated systematic sampling, let's say if I repeat it 2 times, so I would have every 20th of the sample that I selected, but I can repeat it twice. So break the original 1 systematic sampling into 2 systematic sampling. If that's the case, each of the sample would equals to size of 5, but I'm collecting 1 in 20th of the element, and then I repeat it 2 times. So at the end of the day, I still have 2 times 5 10 samples, but I repeat it twice. And then if I repeat it twice, that I would have a different y bar obtained for sample 1 and sample 2. So I would have a distribution of that if I keep repeating the systematic sampling. Okay, so this is the idea. So let's look at the formula first. For the mean, in this case, we could estimate the y bar, which is the mean of means for the repeated systematic sampling. So let's say if originally we only have 1 means of the 10 items, but now I repeat it twice, so I would have 2 y bars. So in this case, I repeat it twice, so I have the y bar 1, y bar 2 adding up together, divided by 2. So I would have the means of means, and we call that this is the y bar under repeated systematic sampling. And y bar I would be the means of the first or the second or the third repeated systematic sampling. And the y bar overall repeated systematic sampling is the mean of the means of each of the yi bar. And the estimated variance. So now I would be able to obtain a different numbers of the y bar. So we can look at the distribution of the y bar from the repeated systematic sampling. So in this case, I can actually calculate the variance of the y bar. So looking at the distance of each of the sample mean to the means of means, taking square over or number of times minus 1. Okay, and then we substitute that as y bar square into the estimated variance formula 5.6, and now we can estimate the variance of the y bar using repeated systematic sampling. So systematic sampling is efficient. That means that should yield a smaller variance when the elements are ordered in a way that there is a large variation within sample, but little variation between sample in terms of the sample mean. So what I mean in here is just repeating what we've just talked about, like from systematic sampling, that would produce a smaller variance estimate, which is more precise if we have the ordered population. And the sample we selected, we want it to be more heterogeneous within the sample, so large variation within the sample, but little variation between samples. That means little variation, so more homogeneous between the clusters. So this is total opposite from these stratifications. For population total, for repeated systematic sampling, it is the same methods. we estimate the y bar using repeated systematic sampling and then multiply to n to have the total. And the variance estimate would be n squared multiplied to the variance estimate from the repeated systematic sampling. Okay, so the next section we want to talk about how we decide how many times of the repeated systematic sampling that we want to repeat. First of all, if we have the population n and we know the kth interval, then we can decide the size of my sample if we collect one systematic sampling. Okay, so now if I want to repeat it ns times, so if that's the case, I want to repeat the systematic sampling. So in other words, the new sample size would equals to my original sample size divided by how many times I want to repeat it, right? So in each of the sample, we will result as a smaller sample size. And the kth interval, in this case, we need to have a further apart of the original interval. So that would becomes k pi, okay? This is a set of formula. You can look it back of how we decide of these intervals of the k pi. So I would like to use example 5.3 to help us understand what's the relationship between the variables are. So let's say if originally I have a sample of a population of 960, and then I would like to collect 60 samples. So using 960 divided by 60, so kth would be 16, right? So 1 in 16 sample, I could select one systematic sample of the size of 60. If this is the case, I can only have one sample, which is, again, we go back to the problem that we cannot obtain the unbiased estimate of the variance because we only have one sample collected. So I want to divide the sample into 10 repeated systematic sample. Okay, so we decided we divide the sample, the original sample, into 10 repeated systematic sample. If that's the case, originally my sample size is 60. I want to repeat it 10 times. So the new sample size would only be 6. The ns is number of repeating times. Now the new intervals originally would be 1 in 16th, but now I want to put that further apart because I want that repeated 10 times. So original 16th is equals to k, but now 16 multiplied by 10, so I would need to put them in 1 in 160th item to be selected, and then each of the sample would have a size of 6. Okay? So that's also explain how we can choose the sample. Let's say the procedures would be I select how many times that I want to repeat it. Let's say ns equals to 10. Select ns starting point from each of the ns systematic sample in the first k elements, and then we can have a random start and then to add k pi, 2k pi, and so on with the random start until the total number of the sample is collected. So let's say we would like to have 10 random starts between the 1 in 160th. Those numbers are randomly selected. If we arrange it in an ascending order, and then we would have the first random start would be the 6th item, and the second random start would be 17th, and then 26, and then 42, etc. Okay, so for the first set of the repeated systematic sample, the first start is 6, and within this sample, the second element would be 6 plus 160, so it would be 166th item, etc., etc. Okay, so we can see